So, good morning, my dear students of fourth semester, and I am dealing with one of the most important unit of your course, that is material science. And under this material science or nanotechnology or nanochemistry, at present I am dealing with the characterization of nanomaterials or nanoparticles. And in my last class, I had discussed about the three important concepts. One is, you all know and you are all aware of this scanning electron microscope, the theory and principle and application. And then I also discussed the transmission electron microscope, and I have prepared a video lecture on STM, that is called the scanning tunneling microscope, under the heading of scanning probe microscope. And in this category, because you all know that in recent years most of the scientists are working on the biological system. Of course, nanocomposites, development of cancer related work, drug development, determination of structure of biological systems. And that technique, fortunately, is one of the revolution, I must say, that is called the atomic force microscopy. Or you can call it, that instrument is called the atomic force microscope. Now it is very difficult for me to discuss the difference between the SAME, TAME, or STM or AFM, because all the techniques are excellent. But there are some specific advantages of this atomic force microscope. So what I am planning today, that within a very, because it is a very, as you know, that most of these topics are very broad, and there are a large number of books are available, good number of research papers are available. But because you know that you are all fourth semester students, and you are all preparing for the examination and other things. So in this small lecture, I will discuss some of the very important principle of atomic force microscopy. What does it mean? And if time permits, I will discuss one or two applications of this atomic force microscopy. But bear in mind that nowadays, of course, cost-wise, it is not very costly as compared to TAME. But it is very, very useful for physics, chemistry, material science, nanobiotechnology, as well as the medical science. So, and most of the scientists are using this spectroscopy. Now, as I have already discussed, that our main objective is the characterization of the nanoparticles. And sometimes you know that whenever we use TAME or SAME, sample preparation is also one of the most important things. And sometimes what happened, if you see the SAME and TAME, so vacuum atmosphere is required. But fortunately here, we don't need type of vacuums and other things. Even simple air or water or liquid or vacuum state, we can study these things. And as I have divided into two parts actually. You know that one is electron microscope, where we use the beam of electrons, and of course different types of lens and electrostatic lens or electromagnetic lens. Here no lens is required, nothing is required. And of course here we will use a probe. That is very important, a very sharp needle type of probes. And there are two types. One is scanning tunneling microscope. I am not saying that there are some limitations of, no. Scanning tunneling microscope is also very good. But there are certain problems and other things, so that we can use that atomic force microscope. And as I have already told you in your first part, it is really a revolutionary invention. And if you just imagine that it can measure 1 into 10 to the power minus 4 angstrom. And most important point here is that here we will study the interaction between that probe and the sample surface. That is our objectives. And we will measure that interatomic force. And again you will see that very low, that is 10 to the power minus 18 newtons. You can imagine such type of force can easily be monitored with the help of these things. This is very common structure, and I have already shown in most of my lectures, because whenever you are talking from the development from the optical microscope, electron microscope, scanning probe microscope, we are always talking about the from photons to electrons. So I will not discuss about this same and tame, because I have already discussed all these things, the HR, what is HR tame, what is FESM. But here our system is the scanning probe microscope, where no lens is required, no electron beam is required, only thing that there is a probe. And there are two types of scanning probe, in fact 3 types we can call it. One is scanning tunneling microscope. Here we are using tunneling current, quantum mechanical tunneling current. And one of the, I should not say demerits, most of the time the substance must be conductive type of natures, because there is a flow of current. But if we are talking about the atomic force microscope, one is scanning probe, it is actually sometimes it is called the atomic force microscope. No current is required like that. And third is, it is not in your course, the scanning near field emission optical, scanning near field emission optical microscope. Okay. So without any delay, today I'll just concentrate only on the atomic force microscope, or AFM. So you know that whenever we talk about the atomic force microscope, there may be a possibility that a question asked that just you classify or compare the same TAME and AFM. So you know that if it is a scanning electron microscope, so there must be a interaction between that sample and that electrons, and there may be different types of scattering. Primary electrons emerge, then secondary electrons, backscattered electrons, and of course sometimes we can monitor the 3-dimensional picture. And these surface properties can easily be studied with the help of the scanning electron microscope. Similarly, you also know about that transmission electron microscope, because it transmits. So internal structure defects can also be calculated or determined. But we will get 2-dimensional picture. But as compared to this SAME and TAME, when we are using that atomic force microscope, we will monitor the force, because when that probe is interact with that sample, there may be some force, and that force can be monitored with the help of course, laser beam and photodiode. I will discuss when I will discuss about the mechanism. But the most important thing is that most of the samples, whether it is a polymers, ceramics, nanocomposite, glass, biological tissues, now people are using for cancer research AFM. So that can be, so therefore every time most of the literature, they say it's a cutting edge, high resolution atomic scale, because if I am talking about the 1 into 10 to the minus 4 angstrom, you can understand the shape of the atoms and other things. So you can understand the importance of that things. Now very short way, just if I compare these things, another important properties of that AFM, that beside the topography, multidimensional topography, it can also determine the different properties. That is one of the most important advantages of atomic force microscope, that several mechanical properties, electrical properties, magnetic properties, optical spectroscopic properties can also be studied with the help of this AFM. And I will show you that how three-dimensional pictures can be imaged, lateral, vertical, horizontal, anything can be determined. And of course, in same also, in our department we are having a same, and we are also using the energy dispersed X-ray, other things. But the sample preparation is very, very simple in AFM. Here, there are some internal structure can also be studied, chemical information, but I am not comparing that which system is best, but every system, हर सिस्टम का कुछ ना कुछ कैरेक्टरिस्टिक है, इसलिए ये बोलना उचित नहीं होगा कि ये सिस्टम बहुत अच्छा है, ये सिस्टम बहुत अच्छा है, ये सिस्टम बहुत अच्छा है. But as per your requirement, as per your research orientation or biological studies, now most of the scientists are using that AFM. लेकिन सिद्धांत दोनों का एकदम अलग है. मैं अभी थ्योरी में आऊँगा. Now, as you know that whenever I teach any subject, it is my habit that I always refer large number of good books, good research papers, and original research paper of this AFM, because the discovery is very important. You know, there is a Nobel Prize in STM and electron microscope, but that is important. So I am just showing you one of the very good research papers published in very good journal, Advances in Atomic Force Microscopy, for probing polymer and properties. And of course, it was discovered in 1986 or 1987. But you see here, that is Chemical Engineering News, you see that there is an application, nanochemistry, thermal properties, electrical properties, morphology, magnetic properties, nanofabrication. So there are a large number of applications. Now, first point is that we must know some very elementary history of AFM. So you must know the elementary history of AFM. And there is a very good correlation between this scanning tunneling microscope. Because you know that these two great scientists of IBM Zurich, you all know the great scientist Dr. Binning and Rohrer, they were actually discovered the scanning tunneling microscope, because there is also a probe, piezoelectric system, everything is there. And they discovered in 1981. But they were awarded Nobel Prize for the monumental work of scanning tunneling microscope in the year of 1986. Along with the father of electron microscopy, you all know that 1930 has already discovered, रूस तीनों को एक साथ मिलके इनको नोबेल प्राइज मिला था. Then after some times, that great Binning went to Stanford University as a sabbatical leave from the IBM and worked with a great professor there. And I think in the same year, 1985 or 86, they were trying to determine the structure of silicon. And during that time, they also developed, of course, for different types of substrate. Substrate may be insulator. In STM, the condition is that the substance must be conductive or semiconductive type of things, because we are applying some current. But for atomic force microscope, that compulsion is not there. So, and another limitation is that STM or TAME or SAME that works under a high vacuum. Here nothing is required, no vacuum is required. Simply we can study these things. So, of course, that Binning is there, but the great professor of Harvard University, Professor Calvin Quet, and another professor. They are also related to IBM, that Garwal, because there are a large number of research papers. I will show you some of the research papers. So who invented atomic force microscope? Although Nobel Prize is for scanning tunneling microscope, but there is no Nobel Prize for that. But both the systems are almost same. Almost, I am not saying that same. Professor Christopher Gerber, University of Basel, Switzerland, and Professor Calvin Quet, University of Harvard, you all know. Actually, he worked with that Gad Binning, and they actually invented, I will not show due to copyright problem, the first machine of atomic force. This is available in the internet. You can see the first machine of atomic force microscope. And now there are a large number of companies, even Bruker, and there are so many Park System, Oxford, Olympus. They are preparing the atomic force microscope. So you can call that in 1985 they have already discovered, but they have published this work in the year of 1986. So therefore I consider that in 1986, the first paper on, this is the original research paper of Gad Binning, Quet, and Professor Jarbar, and they are all from that University of Stanford, but they are actually working in the IBM Zurich. You know IBM and all the things. So this is the first paper, and we are concerned this paper with the measurement of ultra small force on particles as small as single atoms. So we propose to do this by monitoring the deformation of various types of springs and other things. And the title of this research papers is Atomic Force Microscope. So officially, you can sit there. Officially, आप बैठ जाइए. Officially, हम ये बोल सकते हैं कि 1986 में ही एटॉमिक फोर्स माइक्रोस्कोप का डेवलपमेंट हुआ. But as you know that even after 30 years, आप बैठ जाइए वहाँ पे. After 30 years, that professor which is involved in that discovery, Professor Gerber, he also published a very excellent paper in Nature, you know, Nature Nanotechnology, because now if you see the title, आपको समझ में आ जाएगा कि कितना important है. How the doors to the nano world were opened, because the progress of the research depends upon the instrumentation or the infrastructure. जब एक बार atomic force microscope का development is there, then automatically there is a tremendous growth of nanobiotechnology or other things. So paper was written by the Christopher Gerber. And there are large number of review articles, large number of books, large number of study materials available in the literature. It is up to you, and there are some animated pictures are also how that probe is worked. Very nice photographs are also there. But here I am a teacher, so I will just discuss the basic principle behind that atomic force. I will not show you the animated pictures and other things, okay? But आपको समझ में आ जाएगा इसका theory क्या है. But I can request you that you can see those papers, and not very old. 2022, there are some papers 2024, Atomic Force Microscopy in Energetic Materials Research Review. There are some, as I told you, that because there is a tremendous research work in the biological system without disturbing the sample, because most of the biological samples are very soft. So therefore, and after this, there is no disturbance. That is most important. So you see, a beginner's guide to atomic force microscopy, probing for cell mechanics. So there are large number of things. Then there is a very good research articles, Atomic Force Microscopy, 2004. So it's a very good article related to all the diagrams, the basic principles and other things. And those, as I know that I always refer some of the Indian scientists, And this is very very good because मैं आपको हमेशा बोलता हूँ, if you want to learn something for fundamental aspect, you must refer Journal of Chemical Education, American Chemical Society. Similarly, in our country, Indian Academy of Science, Bangalore, they publish the resonance. And the language is very simple, and the whole concept of the atomic force microscopy, I have taken most of the information, diagrams from this article, a tool to unveil the mystery of biological system. Bear in mind, बार बार मैं आपको biological system, I am talking about the biological system. Nanomaterial का बात तो कर रहा हूँ, लेकिन yes, this system is suitable for the biological system, pharmaceutical system, medicinal systems and other things. Now I am coming to that important theory and other things, that atomic force microscope has the ability to image the conductive and non-conductive surface. Anytime you can use any type of tissue or cells, any here, in water or air in water and liquid. And there is a tremendous magnification, over 100 million times. So that is not a big problem. And I have already discussed this point that it can be useful for any types of the material. I will not repeat these things. Now I am coming to the basic theory of this high resolution. How do we get very high resolution, three-dimensional image? Because you know that there is a cantilever, and this cantilever, there is the attachment of a probe, sharp needle, and that needle is approaches to the sample, and then when there is a approach of this needle to the sample, so that there must be some inter-atomic forces. So we have to monitor that inter-atomic forces. Suppose your surface is different types of things. So when this tip approaches the sample, there must be some deflection of that cantilever. मतलब वो cantilever ऊपर नीचे हो सकता है. And that deflection or deformation or bending up and down is to be monitored by a laser beam. जैसा आपका ये ऊपर नीचे हो रहा है, एक laser beam. When we give the laser beam, there is a reflection, and that reflection is monitored by some detector, photo detector and other things. So that is the basic principle. I'll show you the schematic diagram. Now, what is important, you know that it was discovered in 1985 or 1986, and today is 2025. Now, if you see the literature, there are standalone model, entry model, and more advanced model. Sometimes what happened, if you are talking about that tip, if you can ask me, sir, what material is used for that probe and the cantilever? You can ask me. In most of the time, and most of the literature, you will find that cantilever or that probe or needle is made up in silicon chips or silicon nitrides. But you will be happy to know that nowadays people are using graphene, different types of metals, different types of nanomaterials to prepare that tips. And of course, the AFM has a tip which can be modified in many ways to investigating the surface properties. So because sometimes it depends upon the types of the surface. That is important. So it is not necessary that always we use the silicon chips or silicon nitride chips. I will show you one research papers related to different types of chips. Now I am coming to the components of that atomic force microscope. What are the most important components? As I told you, that first point is that there must be some cantilever. Suppose this is a cantilever and that is a probe. Okay, and this is the surface. What I told you that we will monitor the, suppose there is also atoms, tip atoms, here is also atoms. So there is the interaction and we can use some. Now question arises that there are two options. Either the probe is fixed and the sample plate is moving, or sample plate is fixed and the pin is moving. So there is another system. Sometimes it is called the piezo. I will explain each and every components. That is called the piezoelectric scanner. You know, sometimes we applied some electrical field and there is a movement, or due to movement they exert some electrical field. So that piezoelectric scanner can also be used. It's a normal system. So there is a deflection and other things, bending of that cantilever. So there must be some laser beam to monitor these things. Suppose we, so that deflection is, and the theory is that we use the Hooke's law, we use the linear potential. I'll show you the theory behind these things. And so then there must be some this, maybe, and then there are some computer system and loops and other things, and we monitor the topography of that structure. I'll explain it. So first thing is that there must be some cantilever. Second, one tip. Third is laser beam. And detector, everywhere you need a detector. But that detector is very different types of detector, because it can monitor the horizontal deflection, it can monitor the vertical, it can monitor the other types of things, because there may be X, Y and Z type of the things. And computer, piezoelectric scanner and other things. Block diagram is important. Don't worry about the actual photographs of the atomic force microscope. If you see the literature, there are large, although I have written several emails to those companies that please give me the permission so that I can show some of the original photographs of the atomic force microscope. But I have not received any consent from them, so therefore I will not use the original photographs of that atomic force microscope. I am just using the schematic diagram. My students, Abhishek, has prepared a very good schematic diagram. You can understand if you see that schematic diagram. Yes, yes. This is very simple language. Now, as I just told you, that a student may be asked, sir, what is the materials, how probes is prepared. So basically, you know that silicon and silicon nitride, Si3N4, Si3N4. But sometimes nowadays, metal coated probes are also suitable for high resolution, high conductivity, because first point is that it gives atomic resolution. You can understand these atoms and other things. And sometimes different types of metal, iridium, gold, nickel, cobalt, tin, allowing the generation of the nanotubes with the and it sometimes it depends upon the cost, what type of probe you want. Like our same, you have seen that during the purchase they asked me, so what type of detector you want? You want to detect that X-ray? Yes, we can. Do you accept the secondary electrons? Yes, because you know that it's the atomic structure and different types of electrons. There is a bombarding, then electron things are all are based on the quantum mechanics. Bohr's model you all know. But nowadays people are using carbon nanotube probe also. But you can write simply, if you see your books, I've also seen a book, Instrumental Method of Analysis, Willard Mary Dean, or Skoog. I've taken some photographs from that book also. But you see, novel paradigm in AFM probe fabrication. What I want to say, मतलब मैं आपको ये बताना चाहता हूँ कि कोई ज़रूरी नहीं है कि एक ही प्रोब हम लोग यूज़ करें. अलग अलग प्रोब भी as per the requirement, as per the cost, different types of probe can be used. But the principle, there is no change in that principle. That same very small inter-atomic force developed between this tip and that cantilever. और ऊबड़ खाबड़ रास्ता है तो वो आपको up and down, up and down, up and down. I'll show you that structure. So there are three types of mode. One is constant mode, another is static mode, dynamic mode, tapping mode. कौन सा मोड आप यूज करेंगे, ठीक है? And what properties you will monitor? Whether you properties the resonance, frequency, and so there is a change in amplitude. So you can monitor that amplitude. जैसा गड्ढा होगा वैसा आगे वो बढ़ेगा. प्लेन लाइन होगा तो देयर इज नो चेंज. बहुत गड्ढा होगा फिर पिन नीचे आ जाएगा. सो दैट मूवमेंट और द फोर्स डिपेंड्स अपॉन दी सरफेस टाइप्स. कैसा आपका सरफेस है उससे हम लोग मॉनिटर कर लेंगे. दैट इज द पॉइंट. एंड एज आई टोल्ड यू दैट स्कैनर इज वेरी इंपॉर्टेंट because this is the sample and that is integrated with a scanner. And you know that in STM also, I have already discussed the STM. You just see my video lecture of the scanning tunneling microscope. Everywhere we use that piezoelectric scanner. And what is piezoelectric, you all know. I am not going to discuss what is the materials of the piezoelectric and what does it mean. But that scanner is very important because that will decide the movement of that sample table. And again, every system there are a large number of research papers. If you want to learn about the piezoelectric system, so a new precise positioning method for the piezoelectric scanner of APM. So what I mean to say, there are a large number of research papers related to probe, related to different types of system, different types of the model. Okay. But for again and again, for the examination system is that what are the characteristics of AFM, some points, who discovered, working principle, and some application. That's enough. And with some block diagram is very important. That is very important. You have to understand the basic principle of atomic force microscope, basic principle of scanning tunneling microscope. मैं उस दिन आपको समझाया था ना कि क्यों हम उसको टनलिंग करंट बोलते हैं. सपोज टनल, वी प्रिपेयर ए टनल, वेरी स्मॉल करंट ऑफ कोर्स. सो देयरफॉर चूँकि करंट फ्लो हो रहा है तो आपके जो मटेरियल है वो कंडक्टिव मटेरियल होना चाहिए ना. अदरवाइज एक इंसुलेटर होगा तो देयर इज नो यूज ऑफ करंट, एक्सटेंट ऑफ द करंट. बट हियर नो करंट इज रिक्वायर्ड. सो वी कैन यूज ए इंसुलेटर. एक टिश्यू लगा दीजिए एंड टिश्यू को भी वो मॉनिटर कर लेगा. कोई वैक्यूम की जरूरत नहीं है. दैट इज़ द एडवांटेजेस ऑफ दिस. इसलिए मैं AFM को इतना अच्छे से आपको बताने की कोशिश कर रहा हूँ. नाउ द बेसिक ऑपरेशन. फर्स्ट इज दैट देयर इज ए कैंटिलीवर. आई हैव ऑलरेडी डिस्कस दैट and the distance between the cantilever, the probe and surface may be 10 angstrom. So it depends upon the things. There may be a direct contact, there may be a non-touch system, and there may be intermediate vibrations, oscillations are like that. And as the AFM tip moves over the different heights of the deflection of the cantilever, this deflection is tracked by a laser beam. Why? Because if I see that there is a different types of ups and down in the sample, so pins is also ups and down. And naturally weak interatomic forces like van der Waals forces, electrostatic forces, there are some capillary forces, there are a large number of forces. And all these forces, if you know the physics or basic physical chemistry, you can understand that these forces are depends upon the size, the distance between the sample and the tip, 0.1 angstrom, 1 angstrom, 10 angstrom, 100 angstrom, like that. तो वो जो फोर्स होगा वो अलग अलग डिफरेंस होगा. वंडरवॉल फोर्स भी हो सकता है, अट्रैक्टिव फोर्स भी हो सकता है, रिपल्सिव फोर्स भी हो सकता है. एंड so how we monitor this thing? So we just pass a laser beam, and so there is a deflection, and that deflection is monitored by that photodiode. That is also space sensitive photodiode, and then that is converted into image and other things. This diagram is prepared by this Ray block. That is very good diagram prepared by Abhishek, and this diagram is available in the most of the books. So you have to write this diagram. So first thing is that I will not discuss these things. So this is cantilever. If you want to know about the size, shape, diameter, everything is available in the literature. The size of that probe, everything is there. And this is the sample surface, and this is laser beam. So this deflection is monitored by this quadrant photodiode, because it can monitor the changes in x direction, y direction, z direction. 3-dimensional picture can be available. As I told you, maybe vertical, horizontal. One is vertical, one is horizontal, and other is 2. So there are 4, and it is connected with the feedback system, electronics, computer, and other things, sample surface and other things. Now the most important diagram. What is the theory behind of these things? And you know, I think you know that this is a very, very famous theory. That means if there is 2 atoms and radius are different, distance is different, forces are different. One atom is there, one atom is there. So there must be some attraction. But suppose they are very close, so there must be some repulsion. And there is a theory that is called the Lennard potential. You know these things. Lennard potential, attractive force and repulsive force. So the theory behind the whole atomic force microscopy is that very simple theory. That means here you have seen that there may be contact. There is this position, there must be some attraction. जब दूर रहेगा नॉन कॉन्टैक्ट तो कोशिश करेगा नज़दीक आने की. नज़दीक आ जाएगा तो हो जाएगा रिपल्शन. और एक होगा डायनेमिक मोड, फिर कांटेक्ट होगा, फिर आगे जाओ, फिर कांटेक्ट होगा, फिर. सो देयर विल बी सम oscillation, and when there is a oscillation, so there is a change in resonance frequency, automatically I will show you that graph lastly. वो मेरा लास्ट डायग्राम होगा कि कैसे हम उसको मॉनिटर करेंगे. सो yes, that is the most important diagram. And I'll show you that this is not new. The basic theory of I will explain these things. Basic theory is very, very important. You have already studied this thing that is called Lennard-Jones potential. And this Lennard-Jones potential gives the interatomic interaction. Why interatomic? Because there is a probe, there is the atom, surface, there is atom. So that we have to study that interaction, and that interaction depends upon the distance. That interaction depends upon the distance. That interaction depends upon the size. And so same thing we use here. Here we are studying the tip and sample interactions, and we can monitor that potential. We know that r is the distance between 2 interacting particles, probe and sample. Epsilon is the depth of the potential well, and this is the distance with the particle. So what I mean to say that the theory is not new. That great scientists, they explain the principle of atomic force microscopy on the basis of this Lennard-Jones potential. Because I am a teacher, so therefore I am just showing you. You need not to be worried about that formula. But you must know that how do we measure the interatomic interaction between 2 atoms. नाउ देयर आर 3 कंडीशंस. क्या वो एकदम आपके साथ चिपक गया, क्या आपके पास दूर है, क्या बार बार वाइब्रेशन हो रहा है. सो देयर आर 3 मोड्स. नाउ यू शो मी why there are 3 modes. First mode is that suppose it is far from, that tip is far from here, that is called the non-contact mode. This is the normal diagram, just like a normal diagram. Again I have to show this pen. So, anyway, no problem. इनको कर लीजिए, अब इनको समझ में नहीं आएगा. So I'm just a simple diagram. You know, this is the normal diagram, and here is we are monitoring the force and it is distance. And there are 3 conditions. One is non-contact mode. That means it is this tip. Just to understand these things, I will explain individual steps. And this is sample. This is non-contact mode. So it must be at this, actually I have to write this attractive force like that. Non-contact mode. So there is a possibility of attraction, very weak forces. And second is the कॉन्टैक्ट मोड. एकदम इसको अच्छे से आप लोग देख लीजिए, बहुत इजी है, कोई कठिन नहीं है. नो, आई विल नॉट डिराइव एनी मैथमेटिक्स, ऑल्दो वेरी हाई फिजिक्स इज इन्वॉल्व इन दिस थियोरी, वेरी हाई फिजिक्स इज इन्वॉल्व. बट वी आर केमिस्ट, वी आर इंटरेस्टेड इन द एप्लीकेशन ऑफ AFM and the basic principle. That's all. We are not interested in the physics involved in these things. This is contact mode. So that is like that, contact mode. So naturally there is repulsive force. Here, this part is repulsive force. Now the difference between this most important thing, that contact mode and non-contact mode, which is very important. That means here I have written there that if I consider it a contact mode and it is non-contact mode, again you see the difference between distance between the contact mode and non-contact mode. मतलब एक में एकदम जुड़ गया जिसमें कि एट्रैक्शन नहीं हो रहा, रिपल्शन हो रहा है. इसलिए यहाँ पे आई हैव रिटन हियर रिपल्सिव फोर्स, एंड वेयर जहाँ पे दूर है वहाँ उसको खींचने की कोशिश कर रहा है, दैट इज attraction force, van der Waals force. Now the distance between these two, that is most important and dynamic, that is called the tapping mode, TAPPI. ये सबसे important mode है. इसमें आपका ये जैसा ये एटम्स हैं, यहाँ भी एटम्स है, यहाँ पे एटम्स है, ये गड्ढा. सो ये ऑसिलेट करेगा ना, ये ऑसिलेट करेंगे बिकॉज दैट टिप अप्स एंड डाउन, और डिफ्लेक्शन आप बोल सकते हैं ना, डिफॉर्मेशन, बेंडिंग. जैसा सरफेस है, सरफेस का जो वी डू नॉट नो व्हाट इज दिस सरफेस, एज पर दिस सरफेस वो उसका मूवमेंट होगा. जब उसका मूवमेंट होगा, हाउ वी मॉनिटर दैट मूवमेंट? लेजर बीम आ रहा है, तो लेजर बीम आ रहा है तो अलग अलग जो आपका डिफॉर्मेशन हो रहा है, अप डाउन, देयर इज ए डायनेमिक, ये स्टैटिक खड़ा है, आपका सरफेस घूम रहा है with the help of piezoelectric devices. But here, there is a change in oscillation frequency, resonance frequency changes हो रहा है, and that resonance frequency change हो रहा है तो amplitude change हो रहा है, that is monitored by the that photo detector, and that is limb, other point is there, computer system, that will be. So this is the most important diagram of basic theory. इतना आपको करने के बाद आपको लग रहा है कि एकदम सिंपल है. So always remember that there are 3 modes: contact mode, non-contact mode, and intermediate mode, which is important, that is tapping mode, जिसमें आपका काफ़ी फ्रीक्वेंसी इसमें जा रहा है. So लास्ट पॉइंट में हम लोग आ गए हैं. Yes, and now as I told you that 2 theories is very important. One is Lennard-Jones potential, and second is that Hooke's law. You all know that because there is a displacement and other things. When the tip is brought into the proximity of the sample, forces between the tip and sample lead to a deflection of the cantilever. So therefore I am talking about the physics. They can calculate the spring constant because the Hooke's law is F, force is proportional to that x cantilever deflection, and it is, if I just equal, so there is a constant, that constant is called the spring constant. Depending on the situation, force that are measured in AFM include magnetic, capillary force, contact force, van der Waals forces, there are, because all these forces are, as I told, 10 to the power -8, -18 Newton, very small forces, but that force can be measured with the help of, and the displacement of the tip is measured, and a topographical image in 3 dimension, that is very very important. मैंने अभी आपको बताया कि lateral सब कुछ बहुत अच्छे से इसमें दिखाया जा सकता है. So now the operations. I have already told you, first is the contact mode, static mode, where the overall force is repulsive. Non-contact mode, overall force is attractive. The tip of the cantilever does not make direct contact with the sample, but bear in mind that in contact mode there is no chance of change in frequency and oscillation and other things, but in non-contact mode also ऊपर में जरूर है लेकिन उसमें भी थोड़ा ऑसिलेशन के चांसेस है, बिकॉज वहाँ पे देयर इज अट्रैक्शन है, हो सकता है नीचे आ गया एक बार. बट जो टैपिंग मोड है, दैट इज द मोस्ट इंपॉर्टेंट डायनेमिक मोड. द कैंटिलीवर इज ऑसिलेटेड एट हाई फ्रीक्वेंसी, फोर्सेस बिटवीन द टिप एंड सैंपल चेंजेस एज पर द ऑसिलेशंस. जैसा आपका टोपोग्राफी है सरफेस का उसी तरह से. सो टैपिंग मोड इज द मोस्ट इंपॉर्टेंट मोड. इसको थोड़ा डिटेल्स में जाएं. दी AFM टिप इज फोर्स डाउन. कॉन्टैक्ट मोड कोई ज़्यादा बात नहीं है बिकॉज ये रिपल्सन है. दिस मोड इज वेरी कॉमन. द टिप पोजिशन इज कॉन्स्टेंट. लाइक इफ यू जस्ट रिमेंबर द स्कैनिंग टनलिंग माइक्रोस्कोप, देयर आर 2 सिस्टम, कांस्टेंट करंट एंड कांस्टेंट हाइट. आपको याद होगा जब मैं STM पढ़ाया. सो यहाँ पे भी वैसे ही है. दिस मोड इज वेरी कॉमन. द टिप पोजिशन इज कांस्टेंट. द contours of the surface are measured either using the deflection of the cantilever directly or that piezoelectric system that will change automatically. तो टिप वहीं पे है, ये आपका इधर उधर जा रहा है. तो टिप probe is constant but the piezoelectric deflection is constant. So it is a very common mode. Second non-contact mode. It is also very suitable, and of course non-contact mode, there is a position of attractions, and it is very similar to tapping mode and very suitable for the soft sample, and there is the advantages that they will not disturb the sample. Sometimes there is a biological sample, one important point that the sample must not be destroyed. So that is there. Now the last mode is, which is red color I have written, that is the most important mode, because tapping mode is a dynamic AFM technique that image the simple topography by scanning the surface with the oscillating cantilever. And tapping mode operates at the transition between the repulsive and the attractive force, because up and down, up and down, up and down. So contact, non-contact, contact, non-contact. So it will measure all the interatomic forces, starting from van der Waals to electrostatic and whatever the different types of the forces. You see all the forces, van der Waals, dipole-dipole interaction, electrostatic forces, that is most important. In static mode, there is only one type of interaction, but in tapping mode, you can monitor all types of interactions. And a laser beam is used to detect the cantilever deflections. By reflecting an incident beam, we monitor these things. A position sensitive quadrant. Why quadrant? Because it will capture all types of things. I have told you many times, vertical, horizontal, and other types of things. By using a feedback to control the height of the tip above the surface, maintaining constant and laser position and other things. Now I can show you the last photograph. Last thing. Now the application is, I am just showing you that I am not going into details of those applications, but there are many applications, biological and non-biological sciences. And deliberately I have started with the biological system, because AFM is suitable for the biological system. Of course, chemistry, physics, every environmental science is also there, but most important the biological systems. Then differentiate cancer cells and normal cells. There are many research papers are also there. Then of course solid state physics. Then protein structure. Unfolding of the nucleic acid is also studied. Atom and nanostructure manipulation, optoelectronics, surface materials, semiconductor, chemistry of material science, medicine and pharmaceutical industry, environmental and absorption process. Now that the last curve I just want to show you how we study this the tapping mode. Last diagram, just 2 minutes. As I told you, okay, no problem. That tapping mode Okay, so first is no, suppose I am talking about the normal mode. Normal mode, it is amplitude and this is frequency, resonance frequency. Okay. Static mode, so there is no problem. Second, non-tapping, amplitude and frequency. Attraction, non-tapping mode. So you see there is a shift. Third, tapping mode. So you can understand automatically. Same thing, amplitude and resonance frequency. First is static mode, no change. Second, you can monitor the difference between these two. Automatically, you can give the answer. This is tapping mode, most important mode. Black color. Or maybe different types, maybe on this side. So this green color is attraction, attractive force. Black color is repulsive force. So by monitoring this, we can detect this deflection with the help of laser beam and that photodiode, and then it is converted to loop and other things, feedback. So we show the structure, topography of that materials. So now you can understand the difference between the normal static mode, contact mode, non-contact mode. So there is a shifting and it shows the attraction. If it is tapping mode, both things is possible. So all the force can be intermolecular force exert due to the interaction between the tip and that sample. Both the case there are atoms, so there is the interatomic distance can be, so that can be monitored with the help of atomic force microscope. So students very simply, very simple. अभी मैं कुछ फोटोग्राफ्स भी आपको दिखाऊंगा because for the examination point of view, I had discussed the fundamental aspects of atomic force microscope and the general principle of atomic force microscope. Now it is universal truth that this method is very suitable for biological system. and it comes under the scanning probe microscope, and there is a difference between scanning tunneling microscope and this microscope. Basically here we monitor or we study the force, of course there is a weak force that is called the interatomic force between the atom of that tip and the sample. And with the help of these two simple concepts, we can see all the topography of the system. Here I am only showing the 3 points. So I think you have understand these things, and of course you must write a comprehensive literature related to the similarity and dissimilarities between all these electron microscope techniques. Thank you very much.